Hello and welcome back. In the previous video, we described the force that is exerted by a magnetic field on a moving charge. And in that video, we found that if we have a charge Q moving with a velocity v, that the force is going to be equal to QVB sine theta, where B is the strength of the magnetic field and theta is the angle between the velocity vector and the magnetic field. And then we also found that the direction of this force is given by something called the right-hand rule, which we'll go over in just a little bit. Now, hopefully this makes sense that if a magnetic field exerts forces on moving charges, then a magnetic field should also exert a force on a current-carrying wire, since the current that flows through a wire is really just made up of a whole bunch of charges that are moving through this wire. So here, for example, I have these positively charged particles that are moving towards the right. So let's just review the right-hand rule here. Remember that the right-hand rule says that if you orient the fingers on your right hand so that they point in the direction of the velocity, so we want to orient our right hand so that our fingers point towards the right end of the screen, and then you curl your fingers into the direction of the magnetic field. So here, these little X's indicate the direction of the magnetic field. Remember, the X's mean that the magnetic field points into the screen. So I want to orient my right hand so that the fingers on my right hand point towards the right side of the screen, and that when I curl the fingers on my right hand, that they're going to curl so that they point into the screen. And when I orient my hand this way, I can see that my thumb is going to point towards the top of the screen. So each one of these charged particles in this wire has a magnetic force that's pointing towards the top of the screen. And as a result, the entire wire will feel a net force pointing upwards. So how do we actually describe this magnetic force? Well, the idea is that the total magnetic force on the wire is just going to be equal to the sum of the forces exerted on each of the individual charges inside the wire. So if there are n charges inside the wire, then the magnetic force exerted on the wire is just going to equal n times QVB sine theta. And while this is a very nice formula because it's very easy to see where we got this formula from, I just took the formula for the force exerted on a single charge and then multiplied that by n because I have n charges inside the wire. It's not a very useful formula because I don't really have any direct way of measuring the velocity that the charged particles move through the wire or the number of charges inside the wire. So I want to come up with another way to write this formula in terms of variables which we can measure. And hopefully you can see that these quantities n, q, and v are going to be related to the current flowing through the wire, right? So the speed that these charges are moving through the wire and the number of charges in the wire, both of those things should be related to the current. So how do we actually calculate the current that's flowing through a wire in terms of these quantities n, q, and v? Well, the first thing that I want to remind you about current is that if we consider just a very simple circuit like this, we define the current at a particular point in the wire. So we pick a point inside the wire, and then we say that the current is going to be equal to the charge that flows past that point during a time delta t divided by the time delta t. So what I need to do up here with this wire is I need to pick a particular point in the wire, and then I want to calculate the amount of charge that moves past that point during a time delta t. So for this wire, I'm going to pick the right side of the wire as being my point that I'm going to calculate the charge that's moving past this line. And now the trick to calculating this is realizing that if I have a charge over here on the left end of this wire, so let's say this is this charge Q and it's right on the edge of this wire. Because all of these charges, we're assuming that all of these charges are moving at the same speed. So when this charge that started out on the left side of the wire reaches the right side of the wire, any one of the charges that were to the right of this are also going to pass through this point. Now, of course, this wire extends over in this direction, and there are some other charges over here, and they're also moving in the same direction. But the thing about this is that because all of these charges are moving at the same speed, when this charge reaches the right side of the wire, all of these charges that were to the left of this charge Q, they're still going to be to the left of it. So they're not actually going to pass through the right side of the wire by the time that this charge right here that started out on the left makes it to the right end of the wire. So what this means is that the total amount of charge that's going to flow through this right line right here, and the amount of time that it takes for this charge to go from one end of the wire to the other end of the wire is just equal to the total charge that's inside this wire. And that's just going to be equal to, so the current is equal to the amount of charge that flows through this, and that's just going to equal the number of charged particles in this length of wire, so that's N times Q, divided by the amount of time it takes for this charge to move from the left side of the wire all the way over to the right side of the wire. Okay, because the idea is that all of the charges that are in this wire are going to pass through this right side of the wire in the amount of time that it takes for this charge that starts out on the left side of the wire to move towards the right side of the wire. So the current is equal to the total charge in the wire, that's N times Q, divided by that amount of time, and that time is going to be equal to L divided by V. In other words, it's the length of the wire divided by the velocity that this charge is moving at. So the current flowing through the wire is going to be equal to NQV divided by L. So if we go ahead and we compare the formula we found for the current to the formula for the force, remember that that formula is equal to N times the force that is exerted on a single charge, which is QVB sine theta. Hopefully you can see that this quantity, NQV, so this quantity I have underlined here, that's the same quantity that appears in the numerator right here. So I can write NQV as being equal to I times L. So if I plug that into this formula down here, I can see that the force that is exerted on a wire is just going to be equal to IBL sine theta. And now this angle theta is the angle between the direction of the current and the magnetic field. So let's take a look at a couple of examples. This first example says, a copper rod with a length of 0.85 meters is lying on a flat frictionless table. Each end of the wire is attached to an unstretched spring which has a spring constant of 75 newtons. A magnetic field with a magnitude of 0.16 Tesla is directed perpendicular to the table. So remember, these dots here indicate that the magnetic field is pointing out of the screen. And so there's two parts to this question. The first part asks us to determine the direction that the current is flowing through this wire if it's stretching the springs. And then the second part asks us to determine how far those springs will stretch when 12 amps of current flows through this rod. So for the first part, we have to use the right-hand rule to determine the direction of the magnetic force. So remember, the right-hand rule says that if I point my fingers, now I'm going to point them in the direction of the current first. So let's see that we have two options. The current could either be flowing towards the right, or the current could be flowing towards the left. So let's try the first one. So if I point the fingers on my right hand so they point towards the right side of the screen, and then I orient my hand so that when I curl the fingers on my right hand so that they point out of the screen, then I can see that my thumb is going to point towards the bottom of the screen. So in fact, I can see that when the current flows like this through the wire, then the magnetic force is going to point down. And that's exactly what we need, because we're told that these springs are being stretched. Now, if I had assumed that the current was flowing in the opposite direction, then what I would have found is that the magnetic force caused by that would point upwards. So the second part asks us, well, how far is the spring going to be stretched if 12 amps of current flows through this wire? So if this current was equal to 12 amps. So the idea here is that if I draw a force diagram on this little segment of wire, okay, and to be clear, it's this horizontal segment of wire that we're considering right now. So the force that would be exerted on this segment of wire, well, there are two forces that are being exerted on it. There is this magnetic force, which is pulling down on it, and then there are these two spring forces that are pulling up on each end. And the spring forces are going to perfectly cancel the magnetic force. So what we can say is that this magnetic force is going to be equal to 2 times the force exerted by either spring on the two ends. remember that the magnetic force exerted on a wire is equal to IBL times the sine of the angle between the current and the magnetic field. Now if we look back here, my current is pointing towards the right and the magnetic field is pointing out of the page. So there's a 90-degree angle between those two things, and sine of 90 degrees is equal to 1. So we have its IBL times sine of 90 degrees, but this quantity right here is really just equal to 1. And that's going to be equal to 2 times this force that's exerted by these springs on either end, and that's equal to, remember, the spring force is K times delta X. So now if I just solve for delta X, I see that delta X is going to be equal to IBL divided by 2 times the spring constant. And so if I plug this into a calculator, I can see that the spring is going to be stretched by 0.011 meters, so 1.1 centimeters. And the second example says a 0.2 kilogram, 1.6 meter long metal rod is placed on a frictionless ramp which is inclined at an angle of 30 degrees. The ramp has 2 metal strips which supply current through the metal rod. A magnetic field of 0.05 teslas points vertically upwards. And the question asks us to determine the amount of current which must flow through this metal rod in order to hold it in place. So I have a picture here kind of illustrating what's going on. So we have this metal rod which is placed on this frictionless ramp. And as I described in the problem, there are these 2 metal strips running down the length of the ramp, which are at different voltages and cause current to flow through this metal rod. And this magnetic field is going to exert a force on this metal rod, which is going to hold it in place and stop it from sliding down the ramp. So this is kind of an interesting problem because it turns out that none of the forces acting on this rod will point up or down the ramp. However, we'll have components of these forces which will tend to pull the rod either down the ramp or up the ramp. So there are 3 forces that are acting on this rod. There is a gravitational force which points down. And of course, remember that this gravitational force has a component which points into the ramp and a component which points down the ramp. And this component which points down the ramp, we usually call this the x component of the gravitational force, and that's equal to mg sine theta, where this angle here on the left is theta. Now, in addition to this, we always have the normal force, which is going to point perpendicular to the ramp, so that force looks something like this. And then we also have a magnetic force. So the first thing that I wanted to ask was, what direction does the current have to be flowing through this rod so that the magnetic force is going to tend to hold this rod in place? So in other words, we need a component of our magnetic force pointing up the ramp. So if we consider the situation where the current is flowing into the screen, now if we apply the right-hand rule, remember you first orient your right hand so that your fingers point in the direction of the current. So your fingers are pointing into the screen. And then you need to rotate your hand so that when you curl the fingers on your right hand, they're going to point towards the top part of the screen. So when you do that, you should find that your thumb is going to point towards the right side of the screen. So if the current is flowing into the screen, then the magnetic force exerted on this rod is going to point towards the right. And we can see if I decompose this magnetic force into a component that points parallel to the ramp and a component that points perpendicular to the ramp, I can see that the component of the magnetic force parallel to the ramp tends to pull this rod upwards. So we can see that if the current is flowing into the screen in this picture, the magnetic force will tend to cancel the gravitational force. So now the second part of the question asks us to determine how much current is actually flowing through this rod so that the x component of my magnetic force cancels the x component of my gravitational force. And so I'm going to need a little bit of extra room to solve that. So let me go ahead and open up a blank screen. So again, we have a figure here showing the 2 forces that are acting on the rod. Well, actually there's 3, I suppose, because there's also the normal force. But we have this x component of the gravitational force, which tends to cause the rod to slide down the ramp, and then we also have this x component of my magnetic force, which tends to pull the rod up the ramp. And the idea is that these 2 forces, these x components of these 2 forces, have to be equal. So the x component of my gravitational force has to cancel the x component of the magnetic force. So how do I actually calculate the x component of these forces? Well, remember that if I have a gravitational force, this points straight down, this angle right here is going to be 90 degrees minus the angle theta, and then because this is perpendicular to this direction right here, this angle is theta. So looking at this, we can see that the x component of my gravitational force is opposite the angle theta. So that means my gravitational force, the x component of my gravitational force is equal to the gravitational force times sine of the angle theta, because the x component is opposite the angle theta. Now, how do I find the x component of my magnetic force? Well, hopefully you can see that this angle right here is the same as this angle right here. So this triangle right here is similar to this triangle. This angle up here is going to be theta. And so we can see that the x component of my magnetic field, that is adjacent to the angle theta, so it's going to be equal to the magnetic force times cosine of the angle theta. Cosine, again, because the x component is adjacent to the angle theta instead of opposite the angle theta, like we have down here with the gravitational force, where it's opposite the angle. So here I just have to set these two things equal to each other. Remember, the gravitational force near the surface of the Earth is just mg, so we have mg sine theta has to equal the magnitude of the magnetic force times cosine theta, so that's going to be IBL cosine theta. Once again, the angle between the magnetic field and the current is going to be 90 degrees, because the magnetic field is pointing vertically upwards, and my current, remember, was pointing into the screen. So those things are 90 degrees apart. So my magnetic force is just IBL. At sine theta, the angle between the current and the magnetic field is 90 degrees. Of course, we still have this cosine theta because we're just looking at the x component of the magnetic force. And now if I just solve for that current, so if I rearrange this, I see the current flowing through the wire has to be equal to mg sine theta divided by BL cosine theta, or mg divided by BL times tangent of 30 degrees. And if I plug my known values into this, remember the mass was 0.2 kilograms, the length was 1.6 meters, the magnetic field is 0.05 Tesla. So if I plug those values into here, I can see that the current flowing through the wire must be equal to 35.4 amps. Now, the last thing that I want to discuss in this video is the torque that is caused by the magnetic force exerted on a current-carrying loop. And remember that the torque describes the tendency for a force to cause a rotation on an object. And the first thing that I want to do is I want to consider the forces that are exerted on all four sides of this square-shaped current-carrying loop. So I have current that's moving in the direction of these arrows. The magnetic field is represented by these X's. Remember that means the magnetic field is pointing in to the screen. So applying the right-hand rule to this top segment here, remember you orient your right hand in the direction that the current points. So you want to point your right hand so that your fingers point towards the right end of the screen. And then you need to orient your hand so that when you curl the fingers on your right hand, they're going to point in the direction of the magnetic field, which points into the screen. So when you orient your hand like this, your thumb should point towards the top of the screen. So this means the magnetic field exerted on segment 1 points towards the top of the screen. Likewise, if we apply the right-hand rule to segment 2, so I'm going to point the fingers on my right hand towards the bottom side of the screen, and I have to orient my hand so that when I curl my fingers, they point into the screen. And when I do that, I can see that my thumb is going to point towards the right side of the screen. Similarly, if I apply the right-hand rule to segment 3, it's going to point in the opposite direction as it did in segment 1. So now this magnetic force is going to point straight down. And then in segment 4, it's going to point in the opposite direction as segment 2. So this force is going to point towards the left. So looking at this, right away we might just say, well, okay, the total force acting on this object is going to be equal to 0 newtons. And in fact, that is the case as I have it drawn right here. However, we know that even when the net force acting on an object is equal to 0, these forces can still cause an object to rotate. So for example, if I had something like a diamond shape here, and I exert a force which points towards the right on the top part of the box, and a force which points towards the left on the bottom part, even if these two forces perfectly cancel, they're still going to cause this object to rotate around in a clockwise fashion. And this happens because these two forces aren't exerted along a straight line. So what happens here if these two forces which are countering each other aren't on a straight line? And that'll happen, for example, if this current carrying loop is at an angle. So here I have two different pictures kind of showing the same thing. This picture on the left is supposed to be a sort of three-dimensional kind of perspective. So this wire back here, which is current is flowing up through, that's supposed to be in the background, and then this wire over here is supposed to be sort of in the foreground. And the magnetic field is flowing through this loop. Now over here I'm giving you a sort of top-down perspective. So if I were to look at this from the top, over here we have current that's flowing straight up. So if I were looking from the top, that would be current coming out of the screen. Now if we apply the right-hand rule to this point, remember you point the fingers in your right hand in the direction of the current. So that's pointing your right hand so that your fingers point straight out of the screen. And then if you curl your fingers in the direction of the magnetic field, you're going to see that your thumb points directly up. So the force that is exerted on this segment of the wire in this perspective is going to point straight up. Conversely, the force that's exerted on the bottom segment of the wire is going to point straight down. Now because these two forces aren't along a straight line, they're at different points here, they're going to tend to cause this wire to rotate. So here this wire is going to tend to rotate like this. So how do we calculate the total torque that's caused by these two magnetic forces? Now remember that whenever we calculate torque, we need to pick an axis of rotation. So here I'm going to pick the center of this the center of this loop as being my axis of rotation. And if this whole thing has a length L, then my lever arm for both of these forces is going to be equal to L halves. And the total torque that's exerted by these two forces is going to be equal to the torque caused by the force on one end of the loop plus the torque that's caused by the force on the other end of the loop. And these two torques, it turns out, are just going to be equal to each other. Now remember, we calculate torque as being equal to the force that is perpendicular to the lever arm, in this case it's a magnetic force, times the length of the lever arm. Now I've chosen my axis of rotation to be halfway through this thing, so the length of my lever arm is going to equal half of that length L. So here it's going to be L halves. And I'm multiplying that again by the component of the magnetic force that's perpendicular to this. So let me actually draw that component. If this is my magnetic force, the component that's perpendicular to that is this component right here. So it's this component that's perpendicular. And now I've got two of these because I've got this force at the top and I've got this force at the bottom. So we have plus, and then it's the same thing. The component of the magnetic field that's perpendicular times the length of the lever arm, which is L halves. And the force, the magnetic force, is just going to be equal to, this is going to be IBL. That's the magnetic force that's exerted on this. And then we have to think about what that component that's perpendicular. So if this angle right here, if I call this angle theta, let me draw this. So if this angle is theta, then the perpendicular component of my force is opposite that angle. So it's going to be times sine of that angle theta. And then we still have to multiply by the length of our lever arm. And these two forces are going to be equal, so I can just take this whole thing and multiply it by 2, because we have the two forces. And if I rewrite this slightly, I can say this is IBL squared times sine of theta. And L squared, if this is a perfect square-shaped loop, then L squared is just equal to the area enclosed by this loop. So I can alternatively write this as IBA sine theta. And it turns out that the total torque generated by the magnetic force exerted on a current carrying loop is always given by this formula. So here we consider this square-shaped current carrying loop. However, if we considered another shape like a loop, like a circle or something like that, the torque generated by that magnetic force is still given by this formula here, IBA sine theta. And so what this equation means is that the torque exerted on a current carrying loop is going to be equal to 0 when the magnetic field is perpendicular to the current carrying loop. In fact, that's what we saw back at the very beginning when we considered this current carrying loop with a magnetic field that was perpendicular to it. We saw that the net force canceled out, but also the net torque acting on this was equal to 0. However, if the magnetic field is not perpendicular to the current carrying loop, then there will be a torque exerted on this loop. Now, exactly what effect does that torque have? So the question that I want to consider now is what would happen if I took a current carrying loop and I just placed this inside a magnetic field? And so what I have drawn here are several pictures kind of showing you a time lapse of what the forces will be on this current carrying loop. So starting with this first picture here, if I calculate the direction of the force exerted on the bottom part of this loop, so remember we do this by applying the right hand rule, so you first point your fingers in the direction of the current, so that's pointing your fingers out of the screen, and then you curl your fingers into the direction of the magnetic field. In this case, the magnetic field points towards the right side of the screen. And if I do this, I can see that the force that's exerted on this bottom part of this loop is going to point straight upwards. Conversely, the force that's exerted on the top part of this loop is going to point straight downwards. And so hopefully you can see that these two forces are going to tend to rotate this loop around like this, in this kind of clockwise fashion. So at some time later, this loop is going to rotate like this. And the important thing to understand about this is that the direction of these magnetic forces isn't going to change. And the reason is that the two things that are important are the direction of the current and the direction of the magnetic field. And in this case, neither of those two things have changed. My current here is still pointing directly out of the screen. My magnetic field is still pointing directly towards the right. So my magnetic force is still going to point straight upwards, the same as it did in panel 1. So if I look at these two forces together, I can see that they tend to rotate this object in a clockwise fashion. Similarly, in panel 3, my forces are still pointing in the same direction, and they still tend to cause the object to rotate in a clockwise fashion. Now, finally, when I get to part 4, I have a current carrying loop that is perpendicular to the magnetic field. And remember that we found on that previous slide that when the coil is perpendicular to the magnetic field, the net torque on that coil is equal to 0. In fact, we can see that here. These two forces are perfectly canceling each other, and they're not really causing this thing to rotate in one direction or the other. But if we think about this, these forces up here were all causing this coil to rotate in a clockwise direction. So when it gets to this point here, it's got a lot of momentum that's still causing this coil to rotate in a clockwise direction. So it's going to fly past this point, it's going to continue rotating in this clockwise direction, but now when we get to panel 5, these forces that are exerted on the current carrying loop are now opposing the rotation of this coil. So this coil is rotating towards the right, but the torque caused by these two forces is going to oppose that. So let me kind of draw these torques with these green lines. So we have this green torque that's going to point in this opposite direction here. But we have this velocity, or momentum, which is pointing in this other direction. So now my torques are going to tend to slow down this rotation. And so what's going to happen is that this coil here, it's going to keep rotating in this clockwise direction, but it's going to slow down because the forces that are exerted on this coil are now opposing the motion of the coil. So what's going to happen if I place this coil in the magnetic field? Well, basically, the coil is just going to rock back and forth about this point right here where the torque goes to 0. So it's kind of going to look like a torsion pendulum. So if you've ever seen like one of those torsion pendulum clocks, they sometimes call them anniversary clocks, with the masses that just kind of rotate back and forth or rock back and forth. That's what's going to happen here. So this thing's just going to rotate in this direction, and then it's going to rotate back, and then it's going to rotate towards clockwise, and then it's going to rotate counterclockwise. And it's just going to go back and forth like that over and over again. So the one thing that I want to point out about this torque is that it's not a very useful thing, because what I have is I have this coil here, and it's just going to rock back and forth. But the one thing that I really want to point out is that if I could come up with some way to change the direction that the current is flowing through this loop right here at this point 4, then when I got to panels 5 and 6, the torques that are exerted on this loop would continue to point in the same direction. So if I could reverse the direction that the current is flowing through this loop, when I got the panels 5 and 6, the torque would continue to point in this clockwise direction. And in fact, that's exactly what happens inside a DC motor. And so how do we change the direction that the current is flowing through the loop? Well, if we think about this, if we have current flowing through a loop, then that loop must be hooked up to a battery. So we have this wire loop, and then that's hooked up to a battery somewhere, and that battery is causing the current to flow through this loop. And if I could just reverse the connections that are hooked up to this battery when it reached that panel 4, then I would be able to reverse the direction that the current is flowing through this loop. And that's exactly what happens inside a DC motor. So here I have this animated GIF that I stole from How Stuff Works, and it basically just illustrates this idea. So these green lines here, they represent the leads that are connected to this coil, and these red lines here represent the leads connected up to the battery. And what we can see is that as this coil rotates around in a circle, the leads that are connected to the battery are constantly changing. And what that does is it changes the direction that the current flows through the loop, so that the torque is always pointing in the same direction. And so this is exactly what happens inside a DC motor. And so with that, I'd like to end our discussion on the forces that are exerted on current-carrying wires, and in the next video, we'll talk about how magnetic fields are actually created.